there we go. All right. Oh, are we on? Oops. Okay. All right. There we go. So let's see if we can push you a little bit here. What if someone said that you're going to burn aluminum in air? What do you think? Do you think you could write out the balanced equation for that? What do you think? Let's go ahead and try it. We're gonna do a redox reaction, but the burning of aluminum in air. What do you think? Think you could do that? All right. So what do you think I'm going to start with? Aluminum. Okay. And what does burning mean in chemistry? Combined with what? Okay. Now, what do you think? What do you think might form? I remember when I burned magnesium in here, it made magnesium oxide. So it's going to make aluminum oxide. So how do you write aluminum oxide? Really? Don't do that tomorrow. What is it? What's the charge of aluminum? +3. In a compound, it's +3, right? What about oxygen? Okay, so we got that. Now, let's balance it. Oh, wait, can't balance it yet. Got to write the formula right. Now, let's balance it. See how we're reviewing at the same time? We're getting better and better in chemistry. And you see, odd, even. I see an odd, even mismatch. Okay, I'll do that. And what do you think? Pretty good? Are you getting better? All right. Now, do you think this is redox? And, I know you came for some other class, maybe it was Spanish or something. You say, what? Redox? What's that? I forgot already. What does redox mean? Reduction, oxidation, or oxidation reduction, but what does that mean? Right. In a reaction, the driving force was somebody gained electrons and somebody lost electrons, right? That's Leo says Ger. Remember that? Okay, so you are set? Do you think this is oxidation?
Yes.
Okay. All right. So what you do is, how do you know that, first of all?
Because aluminum gained 3 electrons.
Right, and also it's not double replacement, isn't it? So this is a synthesis reaction, so it would be redox. Now, we want to assign oxidation states, and what is an element that's not combined with another element?
0.
All right, and he's not combined with another element either, so everybody get? So you can tell, somebody actually changed their charge, didn't they? All right, so let's do the Leo, let's do they're called half reactions. And by the way, this lesson here, what I've been doing, it's about the 3rd time I've done it, but half reactions are not in your book. I teach this alongside of it. So you aren't going to find this in your book, okay? So let's do a half reaction, and here's what's going to say on the test. It'll say, write out the oxidation half reaction. Write out the oxidation half reaction. And you say, oxidation? That's Leo, isn't it? And then you got to watch your brain. Watch your brain now. If you lose negative electrons, you become what? You become more positive. So who became more positive on the left side going to the right? Aluminum. There you go. And aluminum is going to be who got oxidized, okay? By the way, who got reduced? When you gain negative electrons, you're going to be more negative, aren't you? Who's that? Oxygen, okay. So now I got my characters, don't I? Now, here we go. Aluminum started out with an oxidation state of 0, but what did it turn into? And you look over here and you said, hey, you turned into an aluminum +3, didn't you? How did you do that? How did you go from 0 and jump all the way to +3? How do you do that? If you have the same number of plus and minuses, protons and electrons, how did all of a sudden you jump up to +3? Yeah, lost, right? They lost 3 electrons, isn't it right? Now the reason that we had to put it on the right is because it's a product. This produced this and this. That's why in chemistry the products always go to the right side of the arrow. I know what you want to do. You want to say aluminum minus 3 electrons equals that, but they don't do that because they want to always put the products on the right. All right, now, is everybody okay so far on that? Now we have to fix the numbers. Look at here. Did we really just start with 1 aluminum? How many?
4.
Woo. Well, if each aluminum had to lose 3, and you start with 4 aluminums, what do you think about that? I lost you. If each aluminum had to lose 3 electrons, but you used to really start with 4 aluminums, then you had lost how many electrons? Whoa, 12? Are you with me in this? Okay. But there's one more thing I haven't fixed yet. Did you only end up with 1 aluminum ion? Oh, how many? Oh, 4. All right, are you okay? I'm looking at your faces because that tells me a little bit what's going on. Let's do the GER now. Ready? Oxygen start out at what? 0. And leave a space here. Leave a space. And what did it turn into? Please don't say O3. Don't do it. Don't do it. I know what your eyes see. This thing's made of 2 aluminum ions and 3 oxygen ions, isn't it? So I end up as an oxygen ion with a -2 charge. How do you do that? How do you go from 0 to -2? He must have combined with what? Say it, Dave. 2 electrons. So he must have gained 2 negative electrons. That would do it, wouldn't it? And I keep looking at you, all right? Now we haven't fixed the numbers yet, have we? So let's take a look. Did you really start with just 1 of those? No. What did I start with? Diatomic oxygen. How many? 3. You really did start with 3 diatomic oxygen, didn't you? What'd you end up with? Be careful on this one. What'd you end up with?
6.
How many? 6 oxygen -2 ions. You got that? And the good news is each oxygen had to gain 2, then what would 6 oxygens do? If each oxygen had to gain 2, then what would 6 oxygens do?
12.
Yes, and you know what? You cannot have redox where you lose 12 and somebody else only gains 6. You got that? It's the same 12, isn't it? You cannot lose 12 unless somebody's there immediately to gain the 12, and vice versa. What do you think? And by the way, I want to mention that the only reactions that are never reduced are these because they're half reactions, okay? We do reduce chemical reactions, but this is a half reaction, so we don't reduce that, okay? Otherwise they wouldn't match. See that? They wouldn't match. What do you think about redox? What do you think about half reactions? So if it asks you to look at a reaction and see, what if there are 3 elements? I remember yesterday we had one. Yeah, look at this one right here. Here's an element, here's an element, and here's an element. And we found out that aluminum got oxidized and iron got reduced, but what happened to oxygen? Nothing. So it was not involved. In that case, oxygen was not involved in the redox reaction. What do you think? Are you capable of this? I told you it's a high level chapter. It is, but it seems like you're doing well. All right. What do you think? Okay, so anyway, we only have one more thing to do. It's about a 10-minute lesson. It's a 10-minute lesson, and then we'll be done with anything that has to do with this chapter. And I can't wait to get back into the lab. I do want to get back in the lab. We'll probably spend over a week, and maybe more than that, in the lab. But we do want to get this chapter out of the way. This chapter actually will just be almost everything in this chapter you will do in the lab. There'll be 7 different experiments that you'll do. And I'm hoping that when you do them, you'll say, oh, I get it. This is redox. Or, oh, I get it. This is a precipitation reaction. See it? Okay. All right, what I'm gonna do is, even though I gave you on this handout sheet, your homework sheet, the original sheet that was given for this chapter, it does have this picture on it, and we can use that picture or have another one, either one. So, you wanna use this one since you already have it? Does everybody have this with them? Now, here's what I did with the other class. I actually made another sheet like this, and I gave it to them separately, because some people didn't have it. So I'll tell you what, if you don't have something that looks kind of like that, or if you just want another one anyway, just take one of those, okay? Anyway, I'm gonna teach you in about 10 minutes. There's one more driving force that we haven't talked about in chemistry, and that's what this graph's all about. And you're gonna see this happening in the lab even. So you might want to take one just, if you want. Okay, so what we have is, I don't know if you ever thought about this. I'm not going to get too much into physics, but I asked the other class how many people had heard of the laws of thermodynamics. I couldn't believe that 3 or 4 or 5 students raised their hand. So you've heard of the laws of thermodynamics. Where did you hear that?
Middle school.
Middle school? Wow. Do you remember anything about that discussion? Okay. All right, so I'm not going to get into that very much, but do you remember anything? Did they ever use the word entropy? It's a weird word, entropy. Let me tell you what that is real quickly. If I were to leave my house and no one moved out into the house, and somebody came back 100 years later and looked at my house, do you think my house would be more orderly or more disordered? Would it be more run down or more built up and put back together? And so one of the laws of thermodynamics says that if you don't put energy into a system, things have a tendency to go to states of disorder. If I were to drop a beaker off this table and it fell on the floor, it would be more disorderly, wouldn't it? And that's what's called high entropy. Disorder is entropy. What would you think, though, if you saw all the pieces of that beaker put themselves together? You say, something's not right here. You're right. In the whole universe, we never see, if you don't put energy into a system, you normally don't see it get more orderly, do you? All right, is everybody with me a little bit? Okay, so the fifth driving force has to do with energy changes. Energy changes, okay? All right, now this one, what I'm going to do is I'm going to show you how to read this graph, and I'm going to start right now, and 10 minutes later, I think we'll be able to understand this graph, okay? So just give me 10 good minutes. All right, first of all, some students don't know what free energy is, so let's just get rid of the word free. How about the word energy? Okay, you feel a little better about that? So I got this from a book. I like the diagrams. Let's get rid of that. In order to understand a graph, you always look at the axis first. What I notice here is this thing called reaction progress. What's another 4-letter word I could use to replace that? Reaction progress. What's a 4-letter word I could use to replace that?
Redox.
No? What is it? Say it. That's time, isn't it? When you start a chemical reaction, don't you start with reactants and end with what? And doesn't it take a certain amount of time for that reaction to take place? Even if it's only 100th of a second, it still takes time, doesn't it? So now, I know this is like time, and this is like energy. Okay, now we're not getting too much into physics here. But what I'm going to do is, by the way, even though the author, whoever made this picture, they said reactant, but couldn't it be more than one reactant? Could it be reactants? Okay. So just pretend I have some chemicals that are going to react. Everybody with me? Okay, now what I'm going to do here, I'm going to make up a number. I hereby declare that the total amount of energy in the reactants is about 50 units of energy. So when you go home and you study tonight, you'll say, where did that 50 come from? Where did it come from? I made it up. I just made it up. Okay? I just made it up. You okay with that? So it's like $50. Okay. So the reactants have, they're worth $50, so they have 50 units of energy in them. But look at the products. How much do they have? Huh, they only have 25. Huh, look at that. What do you think about that? What if you went to school with $50 and you came back with 25? What do you think your parents might say?
Yeah, bro.
Where's that $25? Where's the missing $25? Isn't that right? So now let's take a science. What is the science going to say? I have reactants that have 50 units of energy in them, but after the reaction, they only had 25. What's the scientist say? Where'd it go? Where'd the energy go? Where did these 25 units of energy go? And what do you think? Anybody know? Anybody know?
Transferred.
What is it?
Transferred.
One more time.
It was transferred.
I can't hear.
It was transferred.
One more time.
The energy was transferred.
Yeah. Like where? So if I did the experiment in a test tube, would the test tube maybe get hotter? Could that happen? If it was out on the table, could the air get hotter? If it was surrounded by water, could the water get hotter? So what happened to the extra energy? It was given off. It was given off. And so you should have had this word in 9th grade, but what do you call a reaction that gives off energy? Yes. Yeah, you like that word, don't you?
And they're right.
That's very good. So what is exo? X means out, doesn't it? Exit, like exit. This is an exothermic reaction. That means if it happens, it's going to give off energy. I want you to think about this. I'm going to use my hands here a little bit. I want you to think about dynamite. I have dynamite here. And you know dynamite has a lot of high energy bonds, covalent bonds. But then if you spark it, not only will it combine with oxygen, but these molecules will turn into little tiny molecules like nitrogen, N2, H2O, and they don't have hardly any energy into them. So what does that mean? Lots of energy, they turn into something almost no energy. What happened to all the energy? It was given off. And when dynamite gives off energy in a very short amount of time, it heats the air quickly, and the air expands quickly. And you know what it does? It sets up a shock wave. The air expands so quickly, it sets up a shock wave which knocks down buildings, it kills people, it makes holes in the ground, and that's what it was doing. That was a very exothermic reaction, isn't it? Okay. Are you with me so far? Okay, now, so that explains that this is an exothermic reaction. Look at the one on the right. Is it exothermic or not? Some of you have been in school for such a long time. You're saying, I know the game that teachers play. If this was exothermic, then this was, is it? No, it's not. This is also exothermic. How do I know? Because the reactants had what? 50 units of energy, and the products had what? So what? Didn't it lose energy? It was also exothermic, wasn't it? And we'll talk about why these two graphs are different just a second here, okay? All right. Now, you're going to do a lab. One of the labs you're going to do is, I'll say, I want you to make copper combined with oxygen. I have some real copper, and you're going to be looking at it, and the oxygen is in the air, and you look at it, and you look at it, and you look at it, and you say, go ahead. Go ahead. Go ahead, copper. React with oxygen. And it doesn't. Why not? Will copper react with oxygen?
Yes.
Yes. Why it's not doing it?
It's a slow reaction.
It's true. If I let it go long enough, I could get a very, very slow reaction. But what if I want to do it quickly? Yes.
You add a catalyst, something to make it.
All right. And we're going to talk about catalysts in here in just a second, okay? There's something else you're going to do. You're going to put it in a Bunsen burner. You're going to put it in a burner. Now, what's the point of that? Here's the theory. The theory is when oxygen's bouncing around and hitting the copper at room temperature, it's not moving fast enough to make copper oxide. So we're going to heat that copper, and the copper can, and now the copper is really moving. And now when oxygen hits it, okay, copper oxide, copper oxide, copper oxide. And we have a special name for that. What is the energy that you have to put into the system to make the reaction take place? And it's called, this right here, what is it? Activation energy. It just means, hey, you will react, but you won't react unless I heat you. And you're going to find that 2 of the 7 experiments, you're going to have to heat it to get it to react. You'll find in other ones, you don't have to heat it at all. You put zinc and hydrochloric acid, boom, it's ready to go. All right, you okay with this so far? All right, so now let's take a look at the graph. This right here represents another, I'll just make up, and by the way, I'm making these numbers up, aren't I? I'm just making them up. So I had to take the copper, for example, and add 50 units of energy before it got, it says, now I'll combine with oxygen. Whee! Now, not only did I put 50 in, it'll give me 50 back plus more back. And this is how I know it's exothermic, isn't it? So, this is called the activation energy, and that we use Bunsen burners, we might use a microwave, anything to add energy like that. Some people use ultraviolet light. I think your dentist, they have this new kind of stuff with dentistry where you put this stuff in there and then you put ultraviolet light in there and it makes a reaction take place. That's activation energy for them. All right, one more and then we'll be done here. Look at this graph here, and that might be 60. Again, I just made these up. What's different about this graph? And Dave, you were ahead of me, but what's different about this graph? Is it also exothermic? Yes. But what's different? I only had to add 10 units of energy to get it to go. Why is that? Dave, say that word again. What's that word you had?
Catalyst.
Catalyst. Okay, now, here we go. Now, what's interesting to me is, have you ever heard that word before? Catalyst? Okay, so a catalyst is a chemical that speeds up a chemical reaction, but it itself is not a reactant and it's not a product. So if I were to draw a balanced equation for this reaction, where would I put the catalyst chemical? Would I put it on the left or on the right?
Left.
No and no. Whenever you said left, when you said right, I said no and no.
Don't put it in.
Yeah, you do. You put it over the arrow.
Oh.
You put it over the arrow because it's not a reactant, it's not a product, but it's a condition that I need. And so you put it over the arrow. Now, one more time, what's a catalyst? It's a chemical that speeds up a chemical reaction, but it itself is not altered. So one of the labs you're going to be doing is we have this material that I want it to decompose, but it doesn't want to decompose in room temperature. I'm going to put this other chemical in there, which is going to act like a catalyst, and it'll make that thing decompose. But guess what happens when you're done with that test tube? Guess what's laying on the bottom of that test tube? The same chemical that you put in there. It was not altered. Now, when you're in a biology class, I know you can't remember everything, but do you remember the word enzyme? Enzymes. God, when he made cells, there are hundreds and hundreds of reactions taking place every second in your cells. That's unbelievable to me. But they wouldn't take place fast enough if God hadn't also put catalysts in there. And enzymes are catalysts. They make the reaction. You know, enzymes can sometimes break some chemicals down, and other enzymes can build things. That's what they do. Enzymes either break down or build. And guess what? After I break you down, I go over here and break another one down, another one down, another one down, another down. I had the analogy, I heard this once, I liked it. So let's say, I don't know, let's say Dave and Matthew, after school day, I put them each in a room. I say, you can't go home today until you build me a doghouse. Now, each of the rooms have lumber and shingles in it, and nails, okay? And so then, but Dave's room, I put a hammer and a saw and a power screwdriver. And we find out that after about 2 hours or 3, Dave comes out and says, I'm going home. But Matthew's still there 3 days later. Now, so what happened here is the reaction was build a doghouse. You built a doghouse, didn't you? But what happened to my hammer and saw? Is it part of the doghouse? Did it turn into something else? Or could those tools be used again to build another doghouse? But that's an analogy. You know, everybody know what analogy is, right? So that's why catalyst is a chemical that helps a reaction take place at a faster rate, and yet it itself is not altered at all. Okay, so here we go. The theory is that the shape of the catalyst makes the chemicals more likely to come together, and that's what makes it take less what? It takes less activation energy to get it going. So instead of having to heat it really hot to get it to go, maybe a little bit above room temperature. Bang, 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 bang. See that? And that's why it happens at a faster rate. Well, that's actually the lesson right there. And what I'm going to do is I'm going to give you a series of questions. And if you can answer these questions, I think you understand the lesson. Number 1, a catalyst speeds up the rate of a chemical reaction by blanking the amount of blank blank. Who wants to try that? Yes?
By speeding up the amount of, is it energy transfer?
No. Let's try it again. Look at the diagrams. The catalyst, all right. The catalyst speeds up the rate of reaction by blanking the amount of blank blank. Say it again.
Is it by lessening the amount of activation?
Yeah, reducing or lessening the amount of what? Activation energy. Notice that the activation energy here only need a little bit, don't you? Here, I might have to use a bunch of burners to get that much energy, but here, I might be able to even do this at room temperature. Number 2, if the products have less energy than the reactants, where'd the missing energy go? Yes.
Given off.
Yes. And if it happens to be next to water, the water will get hotter. If it's next to a test tube, the test tube gets hotter. If the air, it make the air hotter, like that. Right? What about when you burn wood in a fireplace? Exothermic or endothermic? What? Exothermic for sure, isn't it? Isn't it? Okay. Do you remember this from 9th grade? Anybody know what that is? Anybody know what this is right here? Glucose. What else? What else can I call glucose? Food. Okay. If you're in a coma in the hospital, and I know you have to eat, am I gonna go get a Big Mac, shove it in your mouth, and go like this with your jaw, and try to make it? No, I'll choke you. We're gonna hook a bag up to your arm, and that bag's gonna be a solution of glucose. Hospitals like to call it dextrose. It's a simple sugar. It's glucose. Every cell in your body will survive if you give it glucose. Everybody got that? What's your cell do with the glucose? It combines it with what? What happens to the food in your cells? It starts with a B. What does it mean in chemistry when you combine it with oxygen?
Oxidized.
Burning, okay? So what do you do with food in your body? You burn it. And I'm not going to be a biology teacher, but if you burned it all at once, all your cells would die. But God was pretty smart. He let you burn it a little bit at a time. And remember that thing called the Krebs cycle in the mitochondria? That's what he did. He'll take a little bit of energy out. A little bit, like that. Matter of fact, I'll even store that energy ATPs. So your cells don't burn up, do they? So what was interesting is that not only did you took a high energy compound and turned it into a low energy compound, and energy was given off, wasn't it? Right now, what's keeping your body from getting ice cold? Cellular respiration. Isn't that what this is? Is this called cellular respiration? Your cell's burning fuel, isn't it? Okay. All right. Wait. Let's ask the next question. Is the above reaction exothermic or endothermic? What do you think? Exothermic, right? Next one. This is the hardest one I'm going to ask you. What would an endothermic reaction graph look like? You already have it. What do you think?
I mean, instead of going down, line's gonna go up and heat.
Right,
and
right. You are correct. So here are your products. And I don't know if it needs activation energy, but eventually it's going to end up, if this was 50, this might end up at 70, right? It's the products will end up having more energy in them than the reactants. Let me see how smart you are. Does anybody know something in biology class that did something like that? The products ended up having more energy than the reactants. That means you didn't give off energy, you absorbed energy to make this reaction take place. Look at your faces. I'll give you a clue. It's like the opposite of that. What? It's the opposite of this reaction here. You start with CO2, you start with water, and you add energy, photosynthesis. You are correct. All right. Now, what am I doing? Yes.
Why does it go up and then down?
Well, it doesn't have to, but it might need a little activation energy to get the reaction to go, but it ends up. And you're right. You know what? It could have gone like this. It could have just gone straight up. It's possible. I just put a little bump in there for an activation. Or maybe it didn't need activation energy. I don't know. Now, here's the good news for you. Because I know this is the last part of the chapter, and I know the chapter already has a lot anyway. What I did on your packet is I drew pretty much the same graphs that are going to be on the test. Okay? I'm not saying I'm asking the exact same questions, but the same graphs you're going to see tomorrow. So here we go. Question number 1. Can everybody scan the graphs? What am I looking at here? What is this? Okay. Question 1. Which letter, A through F, shows the product of a reaction? Okay? Write your answer down and I'll ask for a volunteer. Which letter, A through F, shows the product of a reaction? Now don't say anything out loud yet.
Is it multiple letters?
It's got to be, no, it's only one. All right. Now don't say it out loud. How many people you do have the answer? Raise your hand. All right. Who's not ready yet? Who does not have an answer? Okay. All right. Really quickly, give me your answer. Go.
See.
C.
Is that peer pressure?
C.
All right. Does anybody else not want to say C? And you're correct. That is a product, isn't it? That is a product. Go on. Okay, next. Number 2. Which letter, A through F, shows the net gain or the absorption of energy in an endogonic or endothermic reaction? Which letter shows the net gain in energy? Think about it. It has to be an endothermic reaction, though. How many of those graphs are exothermic?
3.
How many of the above graphs are exothermic? 3. There's only one of them that is, see that? All right, well, who ready? Somebody, Leilani, what do you got for a letter on that one?
B.
Which one?
B.
B as boy or D as dog?
D.
C? Dog.
Yeah.
Dog, D. How many people said D? You are correct. Because if the reactant started at this much energy and the products end of this, then that was the net gain of energy. All right, next one. Which letter shows the amount of activation energy needed without using a catalyst? Without using a catalyst. Now, last class missed this one, so you guys are 2 for 2. The last class missed this one. All right, who wants to volunteer? Yes,
E,
which one?
E,
Say it again.
E.
That is correct. This is the amount of activation energy needed without a catalyst, and this is the amount of activation energy needed with the catalyst. Yes? Okay, next one. Which letter shows a reactant or reactants? Which letter shows reactants? Yes, Dave.
Is that A?
It is. It is A. You are correct. All right, what do you think? That was a small lesson, wasn't it? But it did make sense to you? And I wanted to make sure, there's so much else in this chapter anyway. I kind of did, it's going to look kind of like this. I might make different questions, but it's going to look like that. Well, you can't leave yet, but what you can do is if you want